Hello and welcome to my video. Since you're watching, then I can assume that you're here because you're curious about some of the projects in our lab, or you just want to know more about 2D semiconductor devices. So this is going to be a four-part video where I'll be sharing my exciting work on two-dimensional or 2D materials-based field effect transistor technology. And I will be talking about the contributions of my research from fabrication, device modeling, and circuit simulation perspectives. Let me begin by highlighting what 2D materials are. So, when we talk about 2D materials, these are extremely thin film materials with thicknesses in the nanometer regime, and they share three common properties. The most interesting one is that 2D materials are layered materials, and each adjacent layer is held together by a weak van der Waals force. Now, because of this property, it is possible to peel off its layers, allowing us to achieve atomic scale and uniform thickness and dangling bond-free surfaces. Now, 2D materials appear in different levels of conductivity. It can be semi-metallic in the form of graphene or insulating in the form of hexagonal boron nitride, and semiconducting in the form of transition metal dichalcogenide films such as molybdenum disulfide and tungsten diselenide. Now, fabricating and modeling transistors from semiconducting 2D materials will be the focus of this work. So these 2D transistors find several uses in modern electronic applications. The first example is that 2D transistors can be monolithically integrated as top-tier transistors because they can be fabricated at relatively low temperature. Second, because of their mechanical flexibility, they're also suitable for flexible and wearable displays. Finally, since their carrier mobility is preserved at thinner channels, they're also foreseen to extend the scaling limit of transistors. However, there are several challenges in the design of 2D transistors. The most critical one is the contacts. So when a metal is deposited on top of a 2D film, a barrier at the metal 2D junction is usually formed, thereby inhibiting the injection of carriers from the source to the channel and, by translation, the output current of the device. The second one is manipulating the electrical conductivity of 2D semiconducting films. So you can imagine if conventional ion implantation is used, so this high energy process will cause physical damage to the extremely thin film. Lastly, oxide-based gate dielectrics introduce interface states that degrade the mobility of the device as they do not form covalent bonds with the naturally terminated surfaces of 2D films. Now, these challenges are not independent, rather, they are intertwined. Therefore, careful design and processing are needed to meet the necessary device and circuit level requirements and demonstrate the potential of 2D transistors. So, this will be the first issue I will address in this work. Now, what are the design requirements? On the device level, we need N-channel and P-channel devices that are formed using the same type of 2D active film to ensure that we achieve homogeneous material properties. The desirable threshold voltage polarity for the N-FET is positive, while negative for the P-FET. So these complementary devices should further have symmetric performance and high on-off current ratios. So on the circuit level, mainly as a CMOS circuit, the gain should be larger than unity, has rail-to-rail performance, and wide noise margin. So the desirable integration scheme of the complementary devices is that of a homogeneous or monolithic integration, wherein the devices are formed using the same type of 2D active film. So in literature, there are also reports wherein the complementary devices are formed using different kinds of 2D active films, or with only one type of carrier conduction mechanism. So in summary, there are several existing 2D FET integrations in literature, but I want to highlight the columns on their threshold voltage polarity. So most of the works do not possess the desirable polarity conditions because, to begin with, it is unclear what is the condition for threshold in 2D FETs, and this will be the second issue I will be addressing in this work. Now, when we look into the physical structure when fabricating 2D FETs, there are two commonly adopted configurations. So we have the bottom gate top contact structure and the top gate top contact structure. So in this work, I will mainly focus on the source gated or the bottom gated top contact configuration, precisely because of the added control of the gate on the contact region. So because of this gate placement, it is possible to allow carriers to effectively tunnel from the source to the channel, which could potentially yield higher output current. So in such configuration, there are two trajectories of carrier injection that are reported in the literature. So one is aerial and another is near edge. So regardless of these two trajectories, what is important is that carriers need to tunnel through the 2D film body first before they enter the channel. As such, we have to capture the overall shape of the barrier carriers need to tunnel through before they enter the channel. So this is necessary when we model the operation of source-gated 2D transistors. So in order to facilitate the design of circuits based on 2D transistors, we need to describe their operation in a set of mathematical equations, or what we call a compact model. So existing approaches to model 2D transistors include deriving the surface potential solution in the channel, and then deriving the drain current using drift diffusion equations. Another solution is to use traditional silicon MOSFET equations to capture their operation. Now, in these models, however, the source gating effect is not considered. So, in another work, the source gating is considered by proposing a two-path model for the current injection. But the derived model only works for small drain voltages. So the effect of the drain voltage is not captured. So it is important to understand the drain control on the overall shape of the barrier seen by the carriers from the source contacts, because there are varying degrees of drain current dependence observed in fabricated devices. That is, before saturation, the output characteristics exhibit linear, sublinear, or even early saturation characteristics. So the last two issues this work will address are capturing the overall shape of the tunneling barrier as a function of both the gate and drain biasing conditions, and deriving a compact model that will capture the varying degrees of drain current dependence on the drain voltage. So in summary, this research will be addressing four major issues. So first, the challenge of realizing 2D CMOS circuits based on the same active film and with symmetric performance. Second, the lack of a clear definition for the threshold condition of 2D FETs. Third, the incomplete treatment of the overall shape of tunneling barrier into the compact model. And because of this incomplete treatment, the varying drain current dependencies are not fully captured. Therefore, the objectives of this thesis are designed to address these gaps. So the first one is to demonstrate complementary devices based on the same active material with desirable threshold voltage polarity, symmetric current drive, and homogeneously integrate them into CMOS circuits.